Everybody eat?
Yes.
Everybody in the right place?
Yes.
All right, so I want to welcome everybody back from lunch, and we're going to get ready with the next keynote in just a sec. I have 2 or 3 very short announcements, I promise. So number one, don't forget that if you have questions for Jake, you want to tweet those at PyData Seattle. And at the end, I will be, skimming that and using it to, grill Jake based on, whatever it is that all of you are most dying to know. So I'll be watching that as the talk comes to a close. Don't forget there's a social event tonight. There will be food at the social event. So you don't have to go somewhere else and get food. There will be drinks and merriment out in the hallway, sort of leading up to about 6 o'clock. And then I think 6-ish will come in here for food and other fun things to do. And most importantly, if you're staying at the hotel for the conference, there are going to be shuttles that look a lot like that white and green shuttle out there. They will be going from here to Lincoln Square, 1 block from your hotel, if you're staying in Bellevue, from 6 to 8. They may or may not say group. They may or may not say PyData. They will hopefully say at least one of those 2 things. So, just follow other people from the conference, mutter something about, PyData, Bellevue, and, hopefully it'll all work out fine. And if you end up somewhere weird, tweet at PyData Seattle, and we'll definitely catch you by tomorrow's keynote. So there will be shuttles going in the morning as well, picking up the same place they dropped you off. So if you want to use those, that's handy. So tomorrow morning from 8 to 10 a.m., they will be taking you back here. And then there's one last round tomorrow night, but I'm not going to tell you the times now because you'll have long forgotten by then. Okay?
Did you mean hashtag PyData Seattle?
No, at PyData Seattle. So that was a good question. I mean at PyData Seattle. If you tweet at PyData Seattle, I'm going to be reading the tweets that were sent to that account, and I will then use those to figure out. If you do the hashtag, it's just too hard to sift through because there's a bunch of stuff going on. So with all that done, I'd like to introduce Jake. Jake is the director of the eScience Institute at UW. He is an astrophysicist by training and Python developer by day. Jake is known for all sorts of things. You may have seen MPLD3 or more recently Altair, his work on, scikit and, all of the other parts of the PyData ecosystem. You can also find him on Twitter trying to troll statisticians whenever he can. And, with that, I'm just going to let him talk.
All right, thanks very much. Which button? Okay. I think I got it. Yes, excellent. So thanks, it's really great to be here. So PyData is a really fun conference, and over the last 5 years, it's grown immensely. And one thing that happens when you have a whole bunch of new people come into a community is that they may not know the history and may not know all the little details and things. And so what I decided to do with my keynote today was take advantage of this and give kind of a PyData 101, sort of all the things that you may have missed if you're new to the PyData community. And kind of give you some context about where you can start if you're just coming into this, or what packages or what tools you can look into and as you go out and do the work that you have that you want to do in Python. So a little bit about me. I'm Jake VDP. You can find me most places on the internet under that handle. And the most important thing to know about me is these little weenies right here. They've recently replaced Python as my favorite thing to talk about. So feel free to ask questions. They're amazing. But in the Python world, I do a number of things. I have this blog that is being updated much more rarely these days, but kind of fun Python blog. I've contributed to SciPy and scikit-learn and AstroPy and other packages in the space. And I have a few books on Python and on statistics and astronomy and astrophysics and things like that. So you can check some of those out. I'm from the eScience Institute, which is a short little hop across Lake Washington from here. And it's super convenient because getting here from there is only slightly longer than flying from San Francisco, given Seattle traffic. So I got here in like just under 3 hours today. It was great. And we're funded by these 3 organizations, the Moore Foundation, the Sloan Foundation, and the Washington Research Foundation. So I always want to shout out to them because their generous funding has been really helpful in supporting a lot of the Python open source work I've done in the last few years. So thanks to them. So when I'm at the UW, I do a lot of Python training, and I talk to a lot of students who are getting started. And I hear all these sorts of questions over and over again. What is Jupyter? How do I load a CSV? How should I install Python? How do I make my code fast? It's just like endless questions. And there's so many resources out there. You can find answers to all these on the internet, but it's hard to find like one place where you can get these answered. So my audacious goal today is to answer all these questions and more for you in about 40 minutes. And those questions boil down to basically these two things. Why is the PyData space the way it is? Like why is the collection of packages and tools and everything the way it is right now? And that gets back to some of the history of how we've gotten to where we are. And then also, what is the best tool for the job? And that's more about just having kind of a catalog of associations. Like if I want to do this thing, I should look at this tool. So I'm going to do 2 parts of this talk. First, I'm going to delve into the history of how the PyData ecosystem got here. And then I'm just going to do a quick survey of what I think of as the most important kind of fundamental tools in the ecosystem. So one thing to realize as you go into the history of PyData is Python is not a data science language. And this is something that comes to the forefront in all of these issues. If you look at where Python came from, it was created by this gentleman, Guido van Rossum. And it was created in the 80s, and he made it basically as a teaching language. He wanted a good language to teach undergrads. And also he wanted to bridge the gap between the shell and C. Basically say that we want to make things a little bit easier to use on Unix systems. And it's interesting if you ask him about what he thought Python would do. He thought we'd be writing maybe a dozen or a few dozen line scripts. And these days, Python, there are applications with thousands or tens of thousands or hundreds of thousands of lines. I mean, Instagram runs on Python, right? And all these other companies. So it's amazing where Python has come, given that it wasn't really designed to do any of that from the beginning. So really the question to answer is, how did Python become this sort of data science powerhouse, given that it wasn't designed to do that in the beginning? And so I want to kind of dial back and talk about where Python was in certain earlier eras before we are now. And this is kind of the way that I think about it. And in the 1990s, I think of Python in science and data as sort of the scripting era, right? And the motto might be, Python is an alternative to Bash, right? No one wants to code in Bash, so let's code in Python instead. And that's where we were in the 90s. And you have interesting effects of that. And one of the people who was working in the scientific space at that point was this guy named David Beasley, who you may know if you may know from the Python cookbook and other things. But he was working as in a research lab back in the 1990s. And he wrote this interesting paper about scientific computing in Python, where he basically said that scientists are using all these different tools, and they tend to use homegrown software to implement their own domain-specific languages or command line interfaces to put them together. And in this paper, he argued, why don't we just use Python to stitch all these tools together? And he gave a case study of a project he'd been working on for about 4 years, using Python as kind of this glue to script together a bunch of other tools. And he wrote this library that was really influential at that time, the SWIG, Simplified Wrapper and Interface Generator, that could basically parse an entire Fortran or C code and generate a Python interface for you, so you don't have to write Fortran or C anymore to drive your code. And this, a lot of the early SciPy and PyData tools were built on SWIG. My first contribution to scikit-learn was a C++ code wrapped with SWIG. And later on, we abandoned SWIG and moved to Python, but that's another story. So in the 2000s, after that, I think of the 2000s as sort of the SciPy era. And if there's a motto for what Python in science was in the 2000s, it's Python is an alternative to MATLAB, right? For many reasons. And I see some knowing nods in the audience. Yeah, there's many reasons. And if you look at some of the people who are influential in the early 2000s in developing the SciPy stack, you can see this sort of common thread. So John Hunter was the creator of Matplotlib, and a few weeks before he passed away in 2012, he gave this amazing SciPy keynote that I've gone back and watched like 4 or 5 times. But he talks about pre-Python. He had this hodgepodge of work process, Perl scripts that call C++. He had MATLAB, and he got tired of MATLAB and noting it, and started loading things into GNU-plot. And this is what inspired him to build Matplotlib, which is basically a MATLAB replacement in Python, in this language that he wanted to use, rather than all this hodgepodge of other languages. Similarly, you have this guy, Travis Oliphant. He's founded Continuum, and previous to that wrote the NumPy and SciPy projects. And he says prior to Python, he used Perl, and then MATLAB, shell scripts, Fortran, C++ libraries. And he said, when I discovered Python, I really liked the language, but it was nascent and lacked a lot of libraries. I felt like I could add value to the world by connecting low-level libraries to high-level usage in Python. So this is what inspired SciPy. SciPy was this replacement for MATLAB, Fortran, shell scripts, and he wrote that with that in mind. And similarly, if you know the IPython projects or the Jupyter project, this is Fernando Perez. He created IPython, and he had a similar hodgepodge of tools: C, C++, Unix, Awk, Sed, SH, Perl, IDL, Mathematica, Make. This is like horrible to think about what science was like before Python. But what he did is he built this IPython project because he wanted something that was sort of IDL-like or Mathematica-like in the Python space, so he could use just a single tool to replace all these. So you have all these tools that came out in early 2000s that basically had the same goal. All of them, in the early days, they wanted to be the replacement for MATLAB or the replacement for these combined packages. And they all had, if you look in the early code, they all had elements of visualization, they had elements of computation and shell. I mean, if you look at Matplotlib, you can still import the MLab submodule that has things like computing periodograms and things like this. There's still computation in MATLAB, or Matplotlib, even though now a lot of this has been moved out. And the libraries we know today, Matplotlib, SciPy, and IPython, are very, very distinct in what their goals are. So it's been an evolution in the community that way. And so the key conference series I think of for the SciPy era is the SciPy conference. And these are all the SciPy logos I could find online. I looked for the ones before 2008, but they don't seem to exist according to Google. But anyway, so the SciPy conference has really driven a lot of that innovation since 2002 and up to today. A few people I know in this room are going to be at SciPy Austin next week. It's always a really fun conference, and I'd recommend attending if you ever have a chance. So after the 90s, the scripting era and the SciPy era, I think of the 2010s as the PyData era, right? And if there's a motto for the PyData era, it's like, let's use Python as an alternative to R, right? So, and I think we're doing pretty well as a PyData community of offering that. There's still a few things that R does really well that we've not matched. I think one is breadth of statistical routines, another is visualization, but a few of us are working on an answer to that. So the PyData era, I think of it as typified by Wes McKinney and his package Pandas and his book Python for Data Analysis. So this is what he says in the intro to his book. I had a distinct set of requirements that were not well addressed by any single tool. Data structures with labeled axes, integrated time series functionality, flexible handling or arithmetic operations and reductions, flexible handling of missing data, merge and relational operations. And I wanted to be able to do all these things in one place, preferably in a language well suited to general purpose software development. So this inspired Pandas, and I would say arguably we would not be sitting here today if it weren't for the Pandas library and what Wes did in, when was that, 2009 to 2011 or so, when he quit his day job and ate ramen for 2 years so he could work on Pandas all day. So if you ever see Wes, thank him for that, because I think he's really done a huge thing for our community there. But there's other key software that's come out in this era. Pandas, and I think the first big release was around 2011. Scikit-learn had an early guys in 2007, but the kind of main scikit-learn release was 2009 or 2010. Conda for packaging came around in 2012 and really changed the way that I work in Python, changed the way a lot of people do things. The IPython notebook in 2012, and then later on, the IPython project was rebranded to Jupyter. And this Jupyter project has really pushed forward the way that we interact with code, particularly in this community. And of course, the key conference series is PyData, right? You're sitting right here. And the early PyData workshop in 2012, this was a one-day thing at Google in Mountain View. And PyData is close to my heart because my first public Python talk was at that workshop, at that PyData 2012. I gave a 1-hour tutorial on scikit-learn, and from there I was hooked, and I've been trying to attend as many of these conferences as possible. After 2012, they got their branding in order, and they've been pretty consistent since then. But yeah, PyDatas have been all over the world, and it's been this conference series that really has pushed forward this, I think of as data science as something distinct than maybe scientific computing, which is what the SciPy era was all about. And of course, all these eras are concurrent right now. You know, there's people using Python for scripting. There's people using the SciPy tools. There's people using the PyData era. But this is a way that I like to organize, in my mind, how we've gotten to where we are. And that helps you figure out why the tools are the way they are, right? And really, the overarching theme is people want to use Python because of its intuitiveness, its beauty, its philosophy, its readability. Python gets a lot of converts from other languages because it's fun to write. And so what people do is they build Python packages that incorporate lessons learned in other tools and communities. You know, Wes specifically wrote pandas because he wanted to do what R does with data frames. John Hunter specifically wrote matplotlib because he wanted to do MATLAB-style plotting without having to pay for a MATLAB license. You know, we're really, Python is good at extracting knowledge from other tools and other domains and putting them into our own space and then running with them, right? And Python, we've also developed a lot of interesting things of our own. Like, for example, scikit-learn, I think, is, across any language, is kind of the premier way of thinking about machine learning, at least how to interface to machine learning and how to do machine learning APIs. I would argue that no other language has anything that's as succinct and as well thought out as scikit-learn. So, but we have to recognize the whole time through this that Python, again, is not a data science language, and that adds a little bit of complexity at times, right? So Python is this general purpose language, and I actually would argue that the general purpose nature of Python is one of its strengths. You know, Python, you can think of it as a Swiss Army knife. You have Python, you can do all these different things with it. You can do web programming in Django. You can, you know, do all the back-end stuff. You can do front-end type stuff. But over the years, as more and more people use this, the Swiss Army knife gets a little bit complicated, right? And we have all these little tools, and we have to choose which one, and you got to remember the order of them so you can find the one you want. And the strength here is that there's this huge space of capability of what we can do in Python. But the weakness is, like, where do you start? You know, I deeply empathize with new users who say, I want to learn Python right now. And they go out there, and the universe is so huge. There's so many packages and so many things that you have to learn, and so many little unwritten pieces of knowledge that are passed from person to person that it can be tough to break into it. So with that kind of historical perspective of the PyData community, I want to jump now into taking a quick tour of the PyData world. Some of the tools that you've probably used. Maybe if you're newer to the community, you may not have used them. But these, I'm just going to give a quick summary of what I think of as the essential tools today in the PyData world. So for installation, I would recommend going with Conda. So Conda is this, basically, you can think about it as a cross-platform package manager, similar to an apt-get or a yum or a homebrew or a MacPorts type thing. But it works similarly on Linux, OS X, Windows, and lets you install packages, everything you need in basically one click or one command line argument. So it comes in two flavors. There's Mini Conda, which is just the installer, and Anaconda, which is the installer plus hundreds of packages that Continuum thinks you would like. And so I recommend Mini Conda because you can get started. It's a 25 megabyte download, and you can start installing what you need. So if you go to the website, you click on the installer for your platform. It's pretty easy. And then you run it at the command line. There are ways to do this through a graphical user interface as well. And once you have that, you have this program called Conda that has its own Python installation with it. So you have your Python is now connected to Conda. You've completely divorced yourself from your system Python or from any other Python installations. And then you can run commands like conda install and just essentially type the names of the packages that you want. And everything, all the dependencies will be managed. And it's a really, really nice system. If any of you were around the Python scientific world previous to 2012, previous to Conda, things were way more painful, especially if you were in a setting where you were trying to get a room full of people all to get tools on their laptops, and they had Mac and OS X and Windows, and it was, I'm glad we're not there anymore. It was a bad time. It was dark times. The other thing that's amazing about Conda is you can create environments that are basically like sandbox environments to try out new things. So if you do Conda create -n, that means the name. I'm going to call this Py27. I tell it what version of Python I want, what version of the packages I want, and it creates this new environment. And once you activate that environment, you have a brand new Python executable. You have a brand new set of core packages that go with that executable, and you can start using it without breaking your other things. So I use this all the time. This is just the first few environments on my machine. I think I have like 70 or 80. Because every time I'm developing a package, you can see some of them here. Whenever I'm developing a scikit-learn package, I switch to scikit-learn dev and install from master and do the development work there. And then when I need my code to work and not use bleeding edge stuff that might be broken on master, I just switch back to my Python 3.6 environment, right? And you can switch seamlessly back and forth between different Python versions this way. So Conda is huge. I would start there. And if you've heard about this pip thing, there's a whole like pip versus Conda. Pip is another installer for Python packages. It links up to the Python package index. Briefly, the distinction is pip is something that installs Python packages only, and it can install them in any environment. Conda is something that can install any package. You can install Node, you can install R packages, you can install anything, but it only installs them within Conda environments. So that's the distinction I would think about. And if you want to read like 3,000 words on Conda versus pip, I referenced this blog post right here that I did a little while ago. So for your coding environment, once you have everything installed, once you have Conda installed, you can install Jupyter and the Jupyter Notebook. And if you've not seen this, this is huge. This was introduced in around 2012. Actually, the first time I heard about the notebook was at that PyData 2012 meetup. I gave my little my scikit-learn tutorial using a web page and a terminal and like all these different windows. And while I was giving the tutorial, Fernando Perez was in the audience, and he was typing up my entire tutorial into a notebook. It had just been released like 2 months earlier. And he came up after the talk, and he's like, "Hi, I'm Fernando. Have you heard of the notebook?" and he gave me my tutorial in IPython notebook form at the end of the hour, and I've never looked back. Every tutorial since then has been in the notebook because it's amazing. So what you can do is you run this Jupyter notebook, and then you have this web-based platform that's like kind of like a file system accessed through your browser, and you create a new notebook, and then you have an interface where you can start running code, trying different things. You can even embed graphics in line, and you can do a lot with notebooks. Actually, the Python Data Science Handbook that I recently published, I wrote the entire thing in the form of Jupyter Notebooks. So it's almost like a publishing platform. And if you don't feel like buying the book, you can go to my GitHub repository, and all the notebooks are there. If you feel like helping out my kids' college fund, you can buy the book. And as of this summer, actually, I think there's going to be a release today, maybe even. I was talking to the Jupyter Lab folks. There's this Jupyter Lab project, which is like the next iteration of Jupyter Notebooks. And you can think about it as like bringing the notebook into the future, where you have a full IDE with text editor and file viewers and things like this. And I'm really, really excited for what Jupyter Lab is going to do for our community. And I anticipate all my work is going to be in Jupyter Lab within a couple months. It's a really cool project that's coming together. So that's the coding environment and installation. What about numerical computation? If you want to do fast numerics in Python, everything depends on NumPy. And yes, it's pronounced NumPy, not NumPy. Everything depends on NumPy. It's, if you use pandas, or if you use scikit-learn, or if you use any of these other libraries, they tend to base on NumPy and use everything there. So you can conda install NumPy. And then what you have in NumPy is a way to create arrays that you can interact with really efficiently. So you can create arrays. You can do element-wise operations on them. So here, if you do x times 2, it actually multiplies each element of the array times 2. If you take a Python list and do ×2, it doubles the length of the list, right? And then adds all those extra elements. Because it's, Python's designed not for data science, it's designed for something different. So we have these data science tools that we put on top of it. And you can do things like linear algebra. Here's taking the singular value decomposition of a random matrix. You can do random number generation of different things. Down here is some standard normal random numbers. We're taking the fast Fourier transform. So a lot of the sort of core numeric operations you want to do in Python are implemented in NumPy, and they're done really, really, really efficiently. So an example of this is if you're coming from a language like C or Fortran or C# or one of these compiled languages, you might be used to doing things sort of by hand, right? So if you want to take an array of numbers and multiply them all by 2 and add 1, you might be tempted to write a for loop like this, right? That's how you would do it in C if you were writing C code. But in Python, this is really stinking slow, right? This takes 6 seconds to do some basic arithmetic on, 10 million values. This comes down to a number of reasons, but basically it's because Python is interpreted and dynamically typed, and you can get into the weeds about what that means. But the Python implementation, CPython, that most people use, is not great for doing repeated numeric operations because it has to do a lot of type inference. But if you're using NumPy, you can write this much more succinctly, and you can do it a lot quicker. Rather than 6 seconds, this is taking 60 milliseconds. And the way it does that is that the NumPy arrays know about the types of the values, and so it kind of pushes those loops down into compiled code where the type inference doesn't have to be done 10 million times. The type inference is done once on the operation. So anytime you want to do fast numerics in Python, think about this sort of vectorization thing. If you're ever writing for loops over large data arrays, there's probably a faster way to implement your code. And if you want a more complete intro to vectorization and the various guises it takes in the NumPy world, you can. I did this talk a couple years ago at PyCon 2015, and you can look up the video to that. OK, so labeled data. We talked about how pandas sort of opened the PyData era, right? So pandas is this library that essentially implements data frames and relational operators in Python. So it's similar to a NumPy array where you have typed data in these dense arrays, but data frames have labeled columns and labeled indices. And it looks kind of like this. You can add columns to the data frame using Python's slicing or indexing syntax. And you can do things like loading data from disk in a really, really seamless way, in a way that automatically infers all the types of the columns. So if you ever have data on disk and you want to get it into your Python space, pandas is basically the way to go. NumPy has some things like load text and other loading gen from text. Has anyone ever used gen from text? It's horrible. You never want to use it. Pandas basically superseded all of that. And you can do all sorts of interesting SQL-like grouping operations that are really quick. So here's one where we have a bunch of IDs and a bunch of values. And pandas lets you do things like say, I want to group by this ID and take everything with the same ID and sum all the values with that ID. And you get a data frame out that gives you exactly what you want. And this is the kind of operation that you basically can't do in any of the SciPy era tools. Pandas provides that, and that's a new thing. New thing as of, 2010. So yeah, pandas is great. So moving on to the visualization space. If you look up visualization in Python, you probably are going to come up with matplotlib. And that's because matplotlib is just battle tested. It's been around since 2002. Everybody's used it. The Space Telescope Science Institute that runs the Hubble Space Telescope threw a whole bunch of resources into it back in 2004 and 2005. And it's like you can use it for just about anything. So it looks a lot like MATLAB. If you've used MATLAB, you're probably very familiar with it. And many people treat that as a bug these days, but it was definitely a feature when it was created, right? One of the reasons the SciPy ecosystem was able to take off is because it was so seamless to switch from MATLAB to Python. So as people bash Matplotlib, and it's easy to bash Matplotlib for its API and various reasons, but I think we got to keep the historical perspective in mind that we wouldn't be where we are today if Matplotlib didn't have the API that it has, right? So you can plot things, and it's easy to make quite simple plots. If you want to do some other stuff, more complicated things, I would go beyond Matplotlib these days. So if you're doing like data visualization of data frames, Pandas has these really nice plotting routines built in that produce Matplotlib plots without having to do the Matplotlib API. Right, so if you take a data frame and you say data.plot.scatter, and you tell it the 2 column names you want to scatter, it gives you exactly the plot that you want. And there's no need to fiddle with the axis labels and things like this. It just comes out. Seaborn is a similar package. This is a different package that is designed for statistical visualization. And you can do really complicated plots in a few lines of code if you want the types of plots that Seaborn has. So it's a great library to check out. And then beyond Matplotlib, there's also libraries like Bokeh, which gives a lot more interactive features. It can do lots of different plots. I'm not gonna dive too much into that. I just want to let you know that's out there and you should check it out. Another thing is Plotly, which is similar in spirit to Bokeh. It renders plots in the browser, allows you to do interactive visualizations, and has this huge gallery of interesting plots that you can do. So there's a lot out there. And if you're an R user, right? We're in the 2010 era of Python as a replacement for R. The one thing that R has over Python that's really nice is the ggplot library. And I think there's nothing in Python that matches that at this point. One approach to that is this plot9 library, which essentially gives you ggplot's API to produce Matplotlib plots. So that's worth checking out if you're like a ggplot fan and you want to keep using Python. This is not totally mature and complete yet, but I think it's pretty promising. And there's also the Altair library that I'm not going to talk about here, but you can see some of my other talks online on that. Visualization is really complicated in Python. This is a slide from a library, from a talk I gave at PyCon a few weeks ago. And basically every node in that is some library in Python used for visualization. So if you want to see 40 minutes of me talking about this graph, you can go on YouTube and see that. So with all that out of the way, you might want to do some like numerical algorithms, right? So SciPy is the package for doing numerics, and SciPy started as a wrapper of Netlib. Netlib is a whole bunch of Fortran libraries that do things like integration and interpolation and optimization really, really quickly and efficiently. So SciPy contains a lot of these different submodules that essentially are wrappers around these Fortran operations that go really fast. So I can't give examples of all of these, but basically any numerical operation that you want to do, SciPy will have. So like here's an example. We're importing the special library, which is special functions, and we're importing the optimize library. And we can find the minimum of the first order Bessel function and then plot it on there. So this is the kind of thing that SciPy does. It has, especially if you're a physicist, SciPy is great. It has all the routines that you need. If you want to do machine learning, I mentioned scikit-learn. This is a great library because of the API, and I'll show you that. So imagine you have some 2D data and you want to fit a machine learning model. And we all know that a machine learning model is just a fancy way of fitting a line to data, right? So if you're using machine learning to drive a car, you just have a gigantic parameter space, and the line you're fitting to the data is the one that makes the car not crash, right? So if you want to fit a line to data with scikit-learn, you can use this model API where you basically create a model, you fit it to your data, and then you can predict the model on new data and plot it. So this is what a random forest fit to this data looks like. And then if you want to switch out and use a different model, all you got to do is change that model implementation up there. So here I switched from a random forest to a support vector machine regressor. And all you have to do is change out that model definition in the top, and all the rest of the code remains the same. So that's the benefit of scikit-learn. It gives you a single API that lets you explore every single basically important machine learning algorithm out there without having to write a whole lot of boilerplate yourself. So it's a nice way to explore these things, and I think that's a real strength of scikit-learn. And we actually wrote a paper about the scikit-learn API that I think is kind of fun, talking about the choices that were made in defining that in the beginning. So if you want to start doing things in parallel, there's this great library that's maybe a year or two old now called Dask. And Dask is really interesting. If you're doing something in NumPy, this is something you might do. You take an array called A, you multiply it by 4, and remember that it multiplies all the elements by 4. You take the minimum and then you print it, right? What Dask does is it allows you to do the same thing, but rather than actually doing the computation, it just saves the task graph that defines that computation. So when you multiply the array by 4, it says, I want to multiply this array by 4, and it saves that, and it builds up something like this. So we have the data on the bottom, we get the array, and then in 5 different cores, we make the array, we multiply by 4, we take the minimum of all those, and then of course the minimum of the minimums is the minimum, right? So Dask knows about how you can, it knows about associativity of these sorts of operations and aggregations. And so in the end, what you end up with is a way to construct this task graph without doing any computations. And then you can farm that task graph out to anything. That might be multiple cores on your computer. It might be multiple machines in a cluster. It might be something on Amazon Cloud or Azure Cloud. And then at the end, you can compute it. And there's some really cool things happening with Dask in the data science space. There are ways to plug Dask into the back end of scikit-learn to kind of do things transparently. So you can look up those sorts of things, and it's really nice. If you want to optimize code, there's this project that is really, really interesting. It's been around for maybe 5 or 6 years, but it's called Numba, and essentially what it is it's a project that takes Python code and compiles it into LLVM bytecode to make it run really fast, and it's really, really seamless. So let's say you're writing an algorithm that has a big for loop in it. I told you that for loops are bad. You should use NumPy if possible, but some algorithms you can't convert to vectorized code very easily. So if you have a code like this, everyone uses Fibonacci. This takes 2.7 milliseconds to get the 10,000th Fibonacci number. All you have to do is add this Numba just-in-time compiler decorator, and it gives you a 500x speed up in this code. And what it does is it goes through and it goes through and parses all the Python code in there and compiles it to LLVM. Compiles it really quickly, and then for the rest of time, whenever you call that function, you get the fast version of it. And there have been some really nice projects built on top of this. For example, the Data Shader project, which is a visualization project tied to Bokeh. It uses Numba in the back end to do really, really fast visualizations of billions of points. You can see these demos where Data Shader is used to visualize, a billion taxi pickups, and you're scrolling around and zooming and rendering in real time, and that's based on Numba in the back end. Another way to optimize code is Cython. So Cython's something different. It's a superset of the Python language that allows you to compile Python into fast C code. And so an example of this, we take our same fib function here, 2.73 milliseconds for the result. If we run it through Cython, this %% Cython is a way you can do it inside the Jupyter Notebook. You get about a 10% speed up, which, okay, that's sort of fast. And what it's doing is it's taking this Python code, compiling it to C code, and then running the C code rather than the Python code. But to really, really get the benefit of Cython, what you need is to add some types. So if you look at the difference here, all I did was say int n at the top, and instead of a, b equals 0, 1, I did a cdef int a equals 0, b equals 1. So now the compiler knows that these are integers, and it can optimize that code, and you get this 500x speed up just by running your code through Cython with this kind of extra syntactic sugar. And Python it's an amazing project, the fact that it can do what it does. And if you look at the source code of NumPy, SciPy, Pandas, scikit-learn, AstroPy, SymPy, basically any numerical code in the PyData ecosystem is using Python at its core. All these tools are built on top of Python, and that's how you get fast numerics in these libraries. That's how you wrap other C libraries like libsvm in scikit-learn. You use Python to interface to those. So it's a tool if you're doing anything beyond the basic Python development. Check out Python because it's fun. So yeah, that's the extent of the tour that I want to give of all these packages. Hopefully it was helpful, and I tried to put references throughout this slide deck if you want to dig in and get a little bit more. And most of those packages have nice websites with tutorials and things like this. So remember, as you're using Python, that Python's not a data science language. And sometimes that leads to things that are a little bit complicated, right? Sometimes it means that there are a lot of different ways to do things because everyone's trying to build their own API on top of this language that they love. But I think it's also its greatest strength, right? Because we can draw from so many different communities. We can use Python for so many different things beyond data and data science. You know, we're looking back at these different eras of Python development. I think it's interesting, but what's most interesting is thinking about what's coming in the future, right? What are the 2020s going to bring? And even though there are, you know, lots of challenges to Python's sovereignty in the data area, I would say I'm pretty confident that Python will remain relevant for the next 10 years because of the community and the way that people in the community keep adapting things that are learned in other places in the world, bringing them into Python. And so I think all of us are going to be still writing Python in 2029, but we'll see. Thanks very much. So this is my contact info. And we have about 15 minutes maybe for questions, and like Craig said, they're via Twitter, and yeah, thanks.
Yeah, so am I back? Okay. So like I said, tweet at PyData Seattle. I am using very fancy technology where I refresh the page as often as I remember. Hold on, I have to. So the first question that came from a couple different people. You were talking about NumPy.
Yeah.
Is it GIF or GIF?
I'm gonna abstain on that.
Okay. So
I say GIF, but I don't know if that's the answer.
Okay, that's fair.
Although I also say Git and not JIT, so I don't know. And I say JPEG and not JFEG. So.
One of the first ones that came in was, when should I use pandas instead of SQL when both are possible?
Oh, that's a great question. So yeah, pandas is designed to be kind of basically in-core operations. And SQL is a very different thing. You know, you're writing SQL code that can be pushed out to huge databases and do things at scale. So in general, you know, if your data set fits into memory, then use pandas because it's easy. You don't have to spin up a SQL server and figure out all these different things. There are some interesting projects that are trying to like take Pandas API or something similar to the Pandas API and attach a SQL backend to it. So there's various approaches to this that you can look up, but for the time being, I'd say that's the dividing line. Like if you can fit data into memory, use pandas. And for a lot of people, that serves their needs. If you can't fit your data into memory and you still want to use pandas and kind of core Python tools, Dask has a pandas layer that lets you basically do distributed pandas computation across data that's stored on different machines and in different places. So that's something to look up as well.
All right, so the next one, I'm going to go largely out of order. Do you want to comment on open science initiatives? Any thoughts on open science and how it relates?
I like open science. I don't know. So I don't know because there's like actual trademark open science initiative, but is that?
There was no capitals in the tweet, but okay. that doesn't imply much.
Yeah, so one of the things, I'll just say, one of the things that got me into Python, or that's kept me in Python, is the fact that I do a lot of scientific research. And I really think open science is the way of the future, and Python allows you to do that. It allows you, it's free and open. You can put the code out there. You don't have to worry about site licenses for things like if you're doing your work in MATLAB or IDL. So I advocate Python partly because it's so good for open science, especially when I'm in more academic settings.
Another one here. What about this deep learning thing I've heard about?
Well, you might know this little company that's just across the water called Google.
I've heard of that.
Yeah. Deep learning in Python. This is one of the areas that Python, I think, is really excelling in the last few years. And if you look at the deep learning space, I think you can make the argument that Python is the premier language for doing deep learning. A great example of that is the Keras project. I was going to put that in here, but I thought it was a little bit too much. So what Keras does is it kind of provides a nice, clean API that can target different deep learning backends. And right now, I think it targets TensorFlow, which is Google's deep learning code base, and also Theano, which is a project that's been around the Python community for probably a decade, but is sort of like rebranded itself as a deep learning platform because it can do all the things like automatic differentiation and stuff that makes deep learning fast. So if you want to try deep learning in Python, I'd suggest checking out Keras. And there's some really great tutorials. I think there have been some tutorials at PyCon and recent PyData about how to use that.
Next one, you said don't write loops, or don't write for loops given NumPy. Does Numba change that advice?
Yeah, so as I mentioned, you can do some things in Numba with for loops and make them really, really fast. At this point, there's still, using Numba is a little bit of an art. You know, people always put up Fibonacci things like I did and show how it gets a 500x improvement. As soon as you start going into something that's a little more complicated, that has to access data in different places and things like this, it takes a little more trial and error to get the code going really fast. So I think Numba has a lot of potential, and it's been used for some great things already. But if you can avoid Numba and do something that you know is going to work really well, like NumPy vectorization rather than for loop, then I would say that's the first thing you should do. And if you can't vectorize things with NumPy, or if there's a reason, if there's like a memory issue in your vectorizations because NumPy instantiates all the intermediate results, then going to something like Numba or Cython is a good option.
So meta announcement, if you're planning on going to a different session for talk number 2, now's not a bad time to start moving in that direction. I'm going to keep talking, and we're going to keep doing Q&A, but the next talks are going to start, so I don't want everything to run late because you were so excited by these questions, but they're great. So the next one, close to my heart, does Python have an equivalent of dplyr?
Yeah, so that's another thing I think where R wins at this point. There's not, as far as I know, there's not a good dplyr type implementation in Python. But again, I think this is one of those areas where in the coming years you're going to see Python adapt a little more and absorb some of those ideas. So we'll see how that happens.
A very urgent one.
Yeah.
Tabs or spaces?
Tabs or spaces. I of course follow PEP8, which recommends 4 spaces, and that's about it.
There's another one that maybe we can do a play on a common end to podcasts in the Python world. What other packages do you recommend just out in the wild that maybe didn't come up here but are just fun things to check out? Or if you listen to Talk Python to me, he likes to say, what's your favorite thing that nobody's ever heard of that you love on PyPI?
Well, so I'll mention Altair because it's my own thing. This is, I keep talking about how graphics are not up to speed with R and Python, and I think Altair is going to be a good way to address that. It's essentially a way to interface Python to the Vega and Vega Lite grammars. That they're kind of graphical grammars, and they're in the end you end up with a very nice declarative API for doing statistical visualization.
Hold on.
Also, I think one of my favorite packages is the MC package, EMCEE. And it's a really lightweight way to do Markov chain Monte Carlo if you're doing Bayesian inference. So if you're into Bayes stuff, check out MC.
You maybe hinted at this at the end of your talk, but do you have any prediction for what the 2020s will be, the end of your?
Yeah, what the 2020s will be. I don't know, prediction's hard. Especially about the future, is that what they say? Yeah, I think, 2020s, I think we're going to see people using Python more and more for deep learning type things. And if, maybe in 2027, someone will give this talk and say, 2020s were the era of deep learning, where Python was trying to be TensorFlow or whatever.
A topic that you kind of didn't hit, but it does seem pretty important. What about report publishing? What do you do when you finish?
Yeah.
And specifically, do you see good ways that Python integrates with things like, say, Tableau, or do you,
Yeah, so there's different aspects of that. So I'm going to go back to the R community because they've done some great stuff in this area. There's R Markdown, which I really, really like. And I really wish we had an answer to that in the Python world, because it's just a nice way to create documents, to create books, to create blogs and websites. There's another thing in the R world, which is Shiny, which is a way to kind of create web apps, interactive ways to publish your data science results with graphics and interactions on the web. So I think some of the answer to that in the Python world is going to come via Jupyter Lab. Because if you think about what the notebook is, the notebook does give a lot of these elements of like creating interactive visualizations in the browser. But right now they're tied to the notebook, and unless you have the notebook server that you can run, you can't view it without the notebook server, right? But Jupyter Labs is giving this ability to pull out different cells from the notebook and pull out different pieces of the analysis, so that you could imagine, say, running through a whole notebook, taking your last cell that has the interactive bokeh image or the interactive Altair image or whatever, and saying, I want to take this and I want to publish it. And you just have that cell out on a web page with everything in the notebook in the background where the user can't see it. So there's going to be the ability to do that. Another thing that could be interesting is the Plotly team just introduced this package called Dash that's also quite similar to what Shiny wants to do, or what Shiny does, where you can create interactive dashboards in Python, and then in one click publish them up to Plotly's server. And it of course costs some money to put things on their server, but I think it's an interesting package. The package itself is open source BSD license, so there's no reason you have to pay Plotly to use it. So it could be interesting.
RPy2? Question mark? Beaker?
RPy2.
I mean, these were, how do you, I think broadly, how do you pipeline Python alongside other languages? So RPy2 is, this answer for R. Beaker is a notebook that does this for many languages. What are your thoughts?
I know of those tools. I don't use them much because I tend to do everything in Python. But yeah, Jupyter is another thing that allows you to kind of have kernels in multiple languages. I guess I don't have a good answer for that.
Okay. I apologize if I've missed any, but I think I have hit all of the pending questions, and I have 2 different Twitter clients, both refreshing, and they both tell me we're caught up. So
right.
With that, let's go ahead and thank Jake again.
Thanks very much.